Welcome again. This is 𝗙𝗢𝗟𝗟𝗢𝗪 Basic Electronics. In this lecture, we shall try to summarize all the concepts we have learned in the previous lecture, and we shall see some pictorial representation in which we will try to simplify those concepts which we have learned in the previous lecture. So in the previous lecture we discussed about the discrete energy levels in the single separate atom, and whenever the atoms come together in order to make solids, and then those discrete sharp energy levels changes in the energy bands, and those energy bands are separated by energy gaps. And in different atoms we have seen there are different kind of energy bands, and the energy bands are valence band and conduction band, but the formation is different. In some atoms the energy levels are 3s and 3s 2p. In some the those orbitals are mixed, and in silicon there is sp3 hybridization. So for every atom the band which are forming in different orbitals. So this is a separate theory, and we need not to go in this theory. All we need to understand that there are two kinds of bands in the solids: valence band and conduction band. And in the most of the electrons are in valence band, and whenever some electron gets enough energy to break the bond then it leaves its parent's atom and it goes into the conduction band, and now that electron can respond to the electric field, which external electric field which we are applying with the help of some battery or some source. So I think this we have covered in the previous lecture, and now let us systematically summarize all the points one by one. So the point number 1, the electrons in an atoms are arranged in discrete energy levels. As we have discussed in the previous lecture, the electrons are arranged in discrete energy level: 1s, 2s, 3s, 1s, 2s, 2p, 3s, 3p, 4s, 3d. So in this way the energy levels are arranged, and this is according to Aufbau law, and you need not to go in the details of this chemistry, atomic this basic chemistry, and all that is required for understanding this semiconductor physics. We will discuss that. So here 1s is there, 2s, 3s, 2p, 3s, 3p, 4s, and this is 3d. So whatever basics are required from the basic chemistry or the atomic structure, we will revisit them. Okay, so you need not to bother about this thing, but definitely you should be aware of these concepts, and because we cannot discuss these concepts in great detail. Okay, so next point is this: each energy level has some quantum states. As we know, at this energy level we have two quantum state, at this we have two quantum state, at 2p we have 6 quantum states, and again we have 2 in 3p we have 6, at 4s we have 2, at 3d we have 10 quantum states. So the quantum states are at these are the quantum states which are at the same energy level, and for any quantum state the Pauli's exclusion law is this, that it can have only one electron or it can be empty. So electron can occupy these quantum states, and they will start from the first at the least energy level, then the it goes into the next energy level, and this is how electrons fills the all those quantum states. Okay, so the third point is this: in solids, the outer electrons of one atom interact significantly with its neighbor and shifts the energy level of quantum states. Okay, so in solids, the outer electrons of one atom interact significantly with its neighbors and shifts the energy level of quantum state. This we have already discussed. In the interaction of atoms inside the solid and which redistribute the energy levels. Such interaction lead the spreading of sharp energy levels into energy bands separated by energy gaps. This we have discussed. The next point is this: electrons in valence bands correspond to those strongly bonded to the atoms. So in the valence band, the electrons are characterized, which are electrons are in the valence band, the electrons corresponds to those strongly bonded to atoms. So in the valence band, all the electrons are very strongly bonded to the atoms. Okay, and whereas electrons in conduction band correspond to those weakly bonded to atoms. So in the conduction band, those in the electrons in the conduction band are those electrons which were very loosely bound to their parent atoms, and by some elevated temperature or by any other kind of source of energy, by some light source or by some electric field, and those electrons gains the sufficient energy to break the bond, and then those electrons are in the conduction band. And the electrons in the valence band are those electrons which are strongly bounded to the atoms. So this is related to the electrons of valence band and conduction band. So in semiconductors, the conduction band is completely empty at very low temperature. I think at the last point of the previous lecture we have discussed this. At the T equal to 0, this is the absolute temperature. If T equal to 0, then T equal to minus 273 degrees Celsius. This we have already discussed in the previous lectures. So if this is minus 273 degrees Celsius, this is a very low temperature. This temperature cannot be obtained practically at the normal conditions. So we need some cryogenic kind of thing. Have you heard about the word cryogenic engineering? So in that cryogenic engineering, we try to create these temperatures. Okay, so this minus 273 degrees Celsius is not the practical thing. So but theoretically this is true, that at the minus 273 degrees Celsius there will be no electron in the conduction band, and a semiconductor will behave like a insulator, because all the electrons will be in valence band. Because T equal to 0, so there will be no energy. If this is a semiconductor, then there will be no energy, so that any electron can move from valence band to conduction band. So there is no energy available. So this is about the semiconductor. And for and the band gap, so the energy gap is relatively small, and this we will discuss in the subsequent lecture. The difference between the insulators, conductors and solids. This some student was asking this doubt: sir, what is the difference between the insulator and the conductor and semiconductor according to band theory? So first we need to understand band, and then we will come to the those differences, and after understanding this thing, those things are very easy, so it's not a big deal. Okay, so the energy gap is relatively small, say around 3 electron volt. And what is this electron volt? Electron volt is the unit of energy. So what is 1 electron volt? If an electron is accelerating in a potential of 1 volt, so the kinetic energy it gains is the 1 electron volt. If an electron is accelerating in a potential of 1 volt. When the potential is applied is 1 volt, and electron the kinetic energy that electron gains, because definitely the electron will if the electron is here, then definitely there will be some attraction force F equal to QE by this uh, field due to this voltage. So the electron will accelerate. So electron will accelerate, and the energy that electron will gain is called the 1 electron volt. This is the unit of electron volt, and it's a unit of energy. Okay, so 1 electron volt equal to, I think, minus 1.6 into 10 raised to the power minus 19 joules. And I will send you the notes on this electron volt. Okay. And this silicon, now what is this silicon? Silicon is for the silicon the band gap is 1.12 electron volt. For germanium is 0.67 electron volt. In gallium arsenide this is 1.52 electron volt, and this we will try to understand in the subsequent classes. Okay. Okay, welcome. And now we shall start the presentation. Here you can see the it starts from here. Here you can see, no, it starts from here. Okay, so here you can see the 3D model of an atom, and here this is the nucleus of the atom, and the electrons are revolving around the nucleus in various orbits. And this is like just like the planetary system, and its sun at the center, and the various planets are revolving around the sun. Okay, so this is just the 3D model, and this is the simplified 2D model of this 3D model. Here you can see the nucleus and the various orbitals, and then we have the electrons. Here what you need to understand, that the energy of this electron will be less as compared to energy of this electron. So because this and as we are moving away from the nucleus, the energy increases. Okay, and this we have already discussed in the previous lecture. And here you can see the energy of this electron is greater than energy of this electron is greater than energy of this electron, and energy of this electron is greater than the energy of this electron, and again we can say the energy of this electron is greater than the energy of this electron. Okay, and one more thing that we have discussed, that we change the energy in finite steps, which we call the quantums. Okay, so if the electron wants to jump from here to here, electron wants to jump from this energy state to this energy state, then there is a finite amount of energy. There is and the energy in some finite steps is required. So if the electron receives any less energy than that, then electron will transit. Okay, so the energy required must be in the some finite steps. Okay, and this is how the distribution of electron take place. First in the lower energy, then to the next then it occupies the space in the next energy level, and this is how the electrons are distributed in the various energy levels. And here you can see the periodic table, and we are interested in the semiconductors here, and these are the materials that we will study. And here you can see these material belongs to fourth group. These material belongs to fourth group, carbon, silicon, germanium, yes, and tin, lead. So these all are the materials in the fourth group. And why we call these element as a fourth group element? Because in the last orbit of these elements, they have four electrons are in the last orbit. And okay, we shall come to the next picture. And these are the materials in which we are interested: silicon, germanium, gallium arsenide. And you have seen the gallium arsenide energy level in the last slide. So this is a compound semiconductor which is made of group 3 and group 5 elements. So it is used in the LEDs. Gallium arsenide is used in the LEDs. LEDs. There are various other materials we are using, but the basic is gallium arsenide, and our focus will be on silicon and germanium. So what really happens in silicon, and this is how the electrons occupy the spaces in the energy levels. Here you can see this is for silicon, 2 8 4 14 silicon. This is for silicon. This energy distribution is for silicon, and you can see this is 2 and this is 8, and these are I think 2s and 2p combined. So and this is how we are representing the various energy levels, and this is 3s and 3p combined. And that's what we call sp3 hybridization. And these are completely filled, and these are partially filled, and there is a covalent bonding in the semiconductors. And here you can see the atoms which are coming together in order to form the solid, and these atoms are shared. Again you can see 2 8 4, and in the last orbit now you can see the complete octet. Now they have completed their octet by bonding with the neighbor atom. So here you can see this is sharing. In the next slide it will be clear. Here you can see these electrons, these red electrons are the shared electrons, and there is a sharing between this atom and this atom, this atom and this atom, this atom and this atom, and this atom and this atom. So this is how the sharing is happening in the inside the material, and these electrons are shared. These electrons are the electrons which are being shared by these two atoms. So this is how the solid is formed, and the atoms are interacting, and there is a covalent bond between the atoms. And in the next slide again you can these arrows are indicating the covalent bonding, and the next thing is the next thing is the these energy levels, how these electrons in the last orbit which are shared will form an energy level that will be an energy band that will be called as a valence band. That will be called as a these electrons in the last energy level or in the last orbit will form an energy band which is called the valence band. And there will be some empty states, as we know there are higher, or if the 2s is filled and 2p is filled, then definitely there could be some 3s state in which there is no electron, but and that will be empty. So here you can see these are the filled orbits in for these atoms, and here in particular we are discussing with the silicon atom, and these are the filled orbits. You can see there is bonding and these orbits are filled, and there are empty orbits, like for the if this is the silicon atom, then these are the 3s and 3p, and for the and these empty orbits are belongs to 4s orbital. So we need not to go in the details of orbital right now, because as we have concluded in the previous lecture that the energy bands are formed and due to the interaction of atoms when the solids are formed. Okay, and here you can see the energy or empty orbit, and these are the filled orbits. And one thing, and you can see these electrons which are of red color, they won't participate in any of the activity of transition, because these electrons are at a very low energy level, and these are the inner electrons, and only the outer electrons participate, in the atoms, in the transitions. Outer electrons participate, and when the outer electron gains the enough energy, to leave its parent atom, then those atoms move to the conduction band, and when we apply any electric field, then the electron in the conduction band can respond to that electric field. And here you can see there is an energy level, energy band is forming, and because these all are at the almost at the same energy level, and but due to interaction the energy band is forming. And here you can see this is the uh, in between the this is the in between process of energy band. So when the energy bands are forming, and this is what happening in between. Okay, and here now you can see the energy band clearly. This is the valence band, and this is the conduction band. So this picture shows uh, the electrons which are at the outer orbit create some energy levels, and which are called as the valence band. Okay, and this is the valence band, and this is the conduction band, and the gap is called the band gap or the forbidden gap. Why forbidden gap? Because in this gap no electron is allowed, no electron can be in between these two bands. So if any electron gains the energy and sufficient energy to transit, then it goes to the valence band to conduction band, but it cannot be in between the valence band and conduction band. So this is the condition. Okay, and if an electron gains the sufficient energy, then it goes to the valence band. So here I am concluding this lecture, and this band theory is little complex, but with the help of these pictures, and I think you can understand this thing easily. And the basics of this band theory is in the quantum mechanics, and as I already told you, whatever we are talking in the quantum mechanics is gross approximation, and definitely there are equations which govern this behavior, and we know that we need not to go in those details, and because these are beyond of our these things are beyond beyond our syllabus. So we need to confine ourselves with the qualitative analysis. Now we are well equipped with the band theory, and with the help of band theory, and we will try to understand the different things and the question we have asked in the starting of the class about the diamond. We shall try to answer that question. So tomorrow there will be a live class of this subject, and we will have a live class at the timing of our class. So I will send you the link at the Telegram channel, and the link will be sent just 5 to 10 minutes before the class. Okay, so I'm concluding here.